Okay, so here we're going to talk about interpreting correlations in statistics. So researchers sifting through statistical data are constantly looking for meaningful correlations. And the discovery of a new and surprising correlation often leads to a flood of news reports. You may recall hearing about some of these discovered correlations. Dark chocolate consumption correlated with reduced risk of heart disease. Musical talent correlated with good grades in mathematics, or eating less correlated with increased longevity. Unfortunately, the task of interpreting such correlations is far more difficult than discovering them in the first place. Long after the news reports have faded, we may still be unsure of whether the correlations are significant, and if so, whether they tell us anything of practical importance. In this section, we discuss some of the common difficulties associated with interpreting correlations. First one is effects of outliers. So if we examine the scatter plot in the figure, you're going to see you've got a group here and you've got one out here. Your eye probably tells you that there is a positive correlation in which larger values of x tend to mean larger values of y. Indeed, if you calculate the correlation coefficient for those data, you'll find that it is relatively high at r equals 0.880, suggesting a very strong correlation. However, if you put your thumb over the data point, so I'm going to cover it up with my mouse as much as I can, over the data point in the upper right corner of the figure, the apparent correlation disappears. In fact, without the data point, the correlation coefficient is 0. In other words, removing the one data point changes the correlation coefficient from 0.880 to r equal to 0. This example shows that the correlations may be very sensitive to outliers. Recall that an outlier is a data value that is extreme compared to most other values in a data set. So we must therefore examine outliers and their effects carefully before interpreting a correlation. On the one hand, if the outliers are mistakes in the data set, they can produce apparent correlations that are not real, or mask the presence of real correlations. On the other hand, if the outliers represent real and correct data points, they may be telling us about relationships that would otherwise be difficult to see. Note that while we should examine outliers carefully, we should not remove them unless we have strong reason to believe that they do not belong in the data set. Even in that case, good research principles demand that we report the outliers along with an explanation of why we thought it legitimate to remove them. So example 1. You've conducted a study to determine how the number of calories a person consumes in a day correlates with time spent in vigorous bicycling. Your sample consisted of 10 women cyclists, all of approximately the same height and weight. Over a period of 2 weeks, you asked each woman to record the amount of time she spent cycling each day and what she ate on each of those days. You used the eating records to calculate the calories consumed each day. The figure shows a scatter plot with each woman's mean time spent cycling on the horizontal axis and the mean caloric intake on the vertical axis. Do higher cycling times correspond to higher intake of calories? So here we can kind of see we've got kind of a line going that way, a positive correlation. We can see that there's a couple that are not quite on the graph. And we're looking at going from cycling here to the calories per day. It seems like the more they cycle, the more they are intaking. So let's go look at the solution. If you look at the data as a whole, your eye will probably tell you there's a weak positive correlation in which greater cycling time tends to go with the higher caloric intake. In fact, the correlation coefficient is relatively low. R is equal to 0.374. However, notice that the 2 points are outliers, one representing a cyclist who cycled about half hour per day and consumed more than 3,000 calories, and the other representing a cyclist who cycled more than 2 hours per day on only 1,200 calories. It's difficult to explain the two outliers given that all the women in the sample have similar heights and weights. We must therefore suspect that these two women either recorded their data incorrectly or were not following their usual habits during the 2-week study. If we can confirm this suspicion, then we would have reason to delete the 2 data points as invalid. The figure shows that the correlation is quite strong without those 2 outlier points and suggests that the number of calories consumed rises by a little more than 500 calories for each hour of cycling. Of course, we should not remove the outliers without confirming our suspicion that they were invalid data points, and we should report our reasons for leaving them out. So consider how data are grouped. Consider a hypothetical study in which researchers seek a correlation between hours of TV watched per week and high school grade point average, your GPA. They collected the 21 pairs of data values in the table. The scatter plot shows virtually no correlation. The correlation coefficient for the data is about r equal to negative 0.063. The lack of correlation seems to suggest that TV viewing habits are unrelated to academic achievement. However, one astute researcher realizes that some of the students watched mostly educational programs, while others tended to watch comedies, dramas, and movies. She therefore divides the data set into 2 groups, one for the students who watched mostly educational television and one for the other students. So the table shows her results with the students divided into these 2 groups. Now we find 2 very strong correlations, a strong positive correlation for the students who watched educational programs and a strong negative correlation for the other students. The moral of the story is that the original data set hid an important or hypothetical correlation between TV watching and GPA. Watching educational TV correlated positively with GPA, and watching regular TV correlated negatively with GPA. Only when the data were grouped appropriately could this discovery be made. In other cases, the data set may show a stronger correlation than actually exists. Among subgroups, consider the hypothetical data in the table, showing the relationship between the weights and prices of selected used cars. The figure shows the scatter plot. The data set as a whole shows a strong correlation. The correlation coefficient is r is equal to 0.949. However, on closer examination, we see that the data fall into 2 rather distinct categories corresponding to light and heavy cars. If we analyze these subgroups separately, neither shows any correlation. The light cars alone, those are the top 6 in the table, the top 6 one, have the correlation coefficient of r is equal to 0.019. And the heavy cars alone, which are the bottom 6 in the table, have the correlation of negative 0.022. You can understand the problem by looking at the figure. The apparent correlation of the full data set occurs because of the separation between the 2 clusters of points. There's no correlation within either cluster. So you have the cluster of the lightweight and the cluster of the heavy. They really don't correlate. Perhaps the most important caution about interpreting correlations is one we've already mentioned. Correlation does not necessarily imply causality. In general, correlations can appear for any of the following 3 reasons. The correlation may be a coincidence. Both correlated variables might be directly influenced by some common underlying cause, and one of the correlated variables may actually be a cause of the other. But note that even in this case, it may be just one of several causes. All 3 types of reasons are common. Example 2 offers examples of the second and third possible explanations for a correlation, and example 3 shows a coincidental correlation. Caution about causality is particularly important in light of the fact that many statistical studies are designed to look for causes. Because these studies generally begin with the search for correlations, it's tempting to think that the work is over as soon as a correlation is found. However, as we will discuss later, establishing causality can be very difficult. Example 2. Decide which of the three possible explanations is most likely for each of the following correlations. The correlation between infant mortality and life expectancy shown in the figure. Well, the correlation between infant mortality and life expectancy shown is likely a case of common underlying cause. Both variables respond to the underlying variable quality of health care. The correlation between the amount a person smokes and the likelihood of lung cancer. The correlation between the amount a person smokes and the likelihood of lung cancer is causal. Smoking causes lung cancer. And the correlation, that's a negative correlation, between the price of a product and the demand for the product. The correlation between the price and demand is generally also causal. Higher prices lead to lower demand. Example 3. Consider the following real correlation. The stock market tends to rise for the rest of the year. Overall, when a team from the old pre-1970 NFL wins the Super Bowl and tends to fall when the winner is not from the old NFL. This correlation successfully matched 28 of the first 32 Super Bowls to the performance of the stock market, which made the Super Bowl indicator a far more reliable predictor of the stock market's trend than any professional stockbroker during the same period. In fact, detailed calculations show that the probability of such success by pure chance was less than 1 in 100,000. Should you therefore make a decision about whether to invest in the stock market based on the NFL origins of the most recent Super Bowl winner? Well, the extremely strong correlation might make it seem like a good idea to base your investments on the Super Bowl indicator, but sometimes you need to apply a bit of common sense. No matter how strong the correlation might be, it seems inconceivable to imagine that the origin of the winning team actually causes the stock market to move in a particular direction. The correlation is undoubtedly a coincidence, and the fact that its probability of occurring by pure chance was less than 1 in 100,000 is just another illustration of the fact that you can turn up surprising correlations if you go fishing for them. This fact was borne out in more recent Super Bowls. Following Super Bowl 32, the indicator successfully predicted the stock market direction in only 5 of the next 10 years, exactly the fraction that would be expected by pure chance.